honestly, I hope that this was fairly easy. It shouldn't have been very difficult at all to do this. We're going to run through this relatively quickly. It says, answer the following questions in the space provided. Be sure to show all work, include all units and significant figures. Okay? And that's going to be important to us as we go throughout this. So it says, how many milliliters of a 0.250 molar potassium dichromate solution could be prepared from 38.8 grams of solute? Okay? Now, one of the first things I want to make sure that you understand is, what is the solute? Very good, the potassium dichromate, because that's what we had to dissolve to get into a solution. Now, the important thing is that you guys know what the question is. What's the question? Very good. We need to know how many milliliters. That's going to be our question. So they give us a molarity and they give us a gram. Is there a way to get from grams and molarity directly into milliliters? No, this actually takes a little bit of converting, right? So what are we going to need to do? What formula do we need to get to milliliters from molarity and grams? Okay, so we know that molarity is equal to mole per liter, but we don't want that. We want liters is equal to what? Moles divided by molarity. Now that's going to be simple for a little bit, but one thing that's going to be easy, because is there anything given to us that we can plug directly in? What? Okay, 0.250 molar. Now the other part that's going to be challenging is getting this grams into moles. So we've got 38.8 grams. What's the molar mass of potassium dichromate? Okay, and so how many moles does that give us? Now, real quick, who can I pick on? Mary Beth, what is the formula for potassium dichromate? Mary Beth only. Just making sure we're all good on the same page there. Okay, so when we do this, as soon as I plug this into my calculator and I get my answer out, is that going to be my final answer? No, fantastic. What is the answer to this? And now, this does give us liters, and we don't want that. We want to convert that to milliliters, which is what? 528 milliliters. Ah, well done. Very good. Of K2CR2O7. Is there any way you can make it a little more accurate? No. Why, bro? Why did I do that? That's the solution, right? That's the solution we're making. Now, number two, I'm not going to spend the time to do it because I think most of you understand, but I just want to talk out verbally what's going on. So they ask, what is the question? What must be the result? Okay, hold on a second. I have a question. Why is there a desk missing? What'd you do that for? Okay. All right. So how many grams of sodium sulfate are needed to make 600 liter sample of 0.46 molar sodium sulfate solution? So they give you liters and they give you molarity. What was the first thing we do to those values to get to grams? Multiply, and what would that give you? Moles, and then you convert it to grams. But here's my ultimate question: how many significant figures should be in your final answer? 2. Very good. Okay, 39. Sounds good. All right, number 3. What is the concentration of the salt solution if 1.17 grams of NaCl was recovered by an evaporation of 8 liters of the solution? Okay. Now I want to talk about the actual physical thing that went on here. They're asking you for the concentration, right? Which is molarity equals moles times liters. Now, the easy part to do here is to plug in the 8 liters directly, correct? The problem is we've got this, but what I want to talk about has nothing to do with the problem. It actually has to do with this. Recovered by evaporation. So here's what they did, is they took 8.00, right, liters of NaCl aqueous. Okay, and what they did is, do you agree all this is in water, and you have the sodium ion and the chloride ion all dissolved around and being surrounded by water molecules. So what does it mean? And they told you there was how many grams of sodium chloride? Okay, so 1.17 grams of NaCl solid. So what they did is recovered by evaporation. So what did they do to this? Very good. So what they did is they pretty much boiled all the water out of it. Now, because sodium chloride has a higher boiling point than water, if you put it at about 103, 105, would all of the water eventually boil out? Okay, well, if you pull all the piranhas out of the pond, what are eventually those positive and negative charges going to do? They're eventually going to link back up, right? And so what they did is, after they dehydrated the entire solution, now, how long would it take for 8 liters? A really long time, right? This is a large solution. 8 liters would take a really long time to do it. But that's how they figured it out. They completely dehydrated that sample. So when they weighed it in the end, there was 1.17 grams of sodium chloride sitting in the bottom of that beaker. Sure, you could have. It would. Yeah, absolutely. You could have done it at the right temperature where it still would have not molten the other stuff. Like I said, visually, I just want to make sure we're on the same page. So, what do you do with the 1.17 grams of sodium chloride to finish this problem? Convert it to moles and then divide it by 8. How many significant figures do you need? 3, and it gave you an answer of. Say that one more time. Now, how many of you wrote your answer different from that, but you got the same value? Here's what I would have done, honestly. I would have said 2.50 times 10 to the negative third. Write that down for me. You should have done the number of moles divided by the 8. Hang on. This is the part that you guys are gonna have to learn how to adjust. Am I going to be upset with either one of these answers? Absolutely not. But remember, we're playing someone else's game, and because we're playing their game, let's try to put it in terms of their understanding, kind of like that Okie thing you talked about a minute ago. You with me? Okay. So, same concept. These values are the same. There's no difference. One of them is just a little more fancy. And if we can be fancy with it, let's be fancy. And I agree. It's easier to write down the red because that's what shows up in your calculator. I get it. But my rule of thumb is that if you ever have to write 2 or more zeros in front of your first non-zero, convert it to scientific notation. If it were 0.0250, this is acceptable. But again, I'm not going to hound you to the nth degree about it. It's just a suggestion. Anytime you've got to write 2 or more zeros in front of your first non-zero, go ahead and convert it. Because if you wrote 0.0000250, that's just a little absurd. That's a little much. Okay, let's go ahead and let's get in the habit of 2 or more zeros, kick it into scientific notation. What's up? It would be to the negative fifth. Just so we're on the same page, how do you do this? 1, 2, 3, 4, and 5. Because the rule is there must always be one number to the left of the decimal. Just one number. One non-zero. Yes, one non-zero to the left. I'm going to go ahead and tell you this, and it drives me batty, is that you'll see them sometimes do this. 0.250 times 10 to the second. And that infuriates me. I don't know why they do it, but they do it. Sometimes you'll see AP problems like that. It is really dumb, I agree. It's the exact same as your answer. It's the same answer, it's just written a little different. I just didn't roll it one more time to make it a little better. Okay? Alright. Yeah, that one makes me even more frustrated. Times 10 to the negative fourth. Alright, so number 4. This is the one that I think kind of threw you guys for a loop yesterday. What is the molarity? Okay, this is the question. What is the molarity? We know that molarity is equal to mole per liter, and it says of a solution that has this junk. And you read that, and you said, "Wait a minute, that's grams per cubic centimeter." Wait a minute, what do you do here? Okay. This is density, and if you did not write density above this, please write density. Density and molarity are very similar. Very similar. There's one difference in density and molarity. Grams versus moles. That's the only difference. Is when it says something per something else. When you hear that per something. So in this case, it's 10 grams per cubic centimeter. Or you hear concentration, 5 moles per liter. What's always the denominator in that per part? In 1 cubic centimeter. Now, Dustin, I think I may have steered you in the wrong direction yesterday. I did. So here's the crazy part. This is cubic centimeters, true or false? True. Now, we know this fact. 1 gram equals 1 cubic centimeter equals 1 milliliter of water. True or false? True. Well, here's the problem. Mason, you were fixing to step on my toes and take this one out from under me. The problem is, this is grams per cubic centimeter. Molarity is mole per liter. So in 1 cubic centimeter, how many liters do you have? Very good. 0.001 liters. Or 1 times 10 to the negative 3. This is a difficult problem. I agree. Okay? I'm not worried about it. Now, the top part is the easy one. They give you grams, right? But we don't want grams. We need to get that into what? Moles. So I know I'm writing all over this. So I've got 10.0 grams, and this is a solution of lead 2 acetate. What was the mass of lead 2 acetate? It should be really big. 325.3 grams in 1 mole, which gives me how many moles? 0.307 moles. So that technically would have been the calculation of your molarity. Say that one more time. Hold on 1 second. Let's just kind of absorb it for just 1 second. One more time. We know molarity is mole per liter. They give you grams per cubic centimeter. The grams to mole part, the top, that's pretty self-explanatory. The bottom part is, I think, where the wheels kind of fall off. When it says per something, per liter, per cubic liter, per whatever, do you agree that it's always 1? Well, the problem is that this is 1 cubic centimeter. Well, what do we dissolve that lead 2 acetate in? In water. Well, 1 cubic centimeter is equal to what? 1 milliliter. So essentially, this is kind of like saying 1 milliliter. Well, why can't that work for solving for molarity? Because it's liters. Okay? So, what we did is we converted 1. Now, remember, King Henry died at a bar drinking chocolate milk. At a bar. Because you can, and you know, a lot of people say King Henry died by drinking chocolate milk. I don't like by because it's not a very emphatic enunciation enough for you to realize that the by means something. You just say King Henry died by drinking chocolate milk. Like, the by doesn't stop you. But when you say King Henry died at a bar, like, it's enough to say, wait a minute, that's important. Do you see the difference? I understand that, but so does at a bar. And because you draw a line. It's a bar. What? What did you do? Okay, so here's the deal. So if this is 1, and we're starting at milli, what way does my decimal got to roll? 1, 2, 3. So if we're 1, 1, 2, 3, and so what do I fill in? 0. Okay, so that's why, Nicole, This turns into 0.001. Does that make sense now? Okay. So now we're on the same page? Okay. Jamila, you good? Okay. Basic question? Yeah. That's where that 10 came from. See how it feels sometimes when I grade y'all's work? We changed it to moles. Go ahead. What color are you looking at? Okay. What about it? All right. If I know the density of a solution, I can determine the concentration of that solution. Because do you agree that density is mass per volume? Okay. Molarity is mole per volume. You with me? The mass to mole is easy. Do you agree with that? The top is easy. Okay. The bottom part is the tricky part. Because molarity is mole per what? Liter. The density given was gram per what? Cubic centimeter. The reason that's a problem, do you agree when we say something per something else? The per means for one. So this is there are 10 grams in every 1 cubic centimeter. Do you agree with that? Okay. That is where that came from. Yep. And then the reason that this does not work is because this is cubic centimeter and we have to get it to liter. So that's the conversion. Yes. Yep. Go ahead. Okay. Yes, and let me pause you. The way that we understand that is if you it's how you read the unit. It's 10 grams for every 1 cubic centimeter. Okay, go ahead. Exactly. Yes. Yes. Exactly. So let me ask you this: what if I gave you 2 cubic centimeters? How many grams would you have? Exactly. It's proportional. Does that make sense? If you've got, all right, Jamil, it's the density means for 10 grams fit in 1 cubic centimeter. One where? That's for water. That's for the volume. Just water. Does that help now? Well, if the density were 10. Yeah, it's always going to be per one. So, but if the density is 10, and I give you 20 grams, that means it takes up 2 cubic centimeters. Oh, we're done. All we have to do is give me the answer. Yeah, all right, what's the answer? What's the concentration? Wow. Yes. Very good. Right. So that's a really high concentration, in fact. An extremely high concentration. I bet you didn't roll the liters, did you? 307. That's wrong. Okay, I'm tired of it. I'm tired of this problem. Y'all figure it out. I'm tired of the problem, sir. No, just high five. I didn't. I just showed you what the density was, what we had to convert it to. So it's 10 grams for 1 cubic. I converted my 10 grams to moles, and I converted my 1 cubic centimeter to liters. That's all I did. Okay. Yes, sir. Yes. Because there's a lot of particles in a certain amount of solution. It's a high concentration. All right, so number 5. You are given 515 milliliters of a zero point 0.2 molar ethanol solution. How many grams are in the solution? How many molecules of ethanol are present? And what volume is dissolved in water if ethanol has a density of 0.789 grams per milliliter? This is a lot. I want to do this whole problem with you guys. All right, so let's start with part number 1. They give you a volume and they give you 200 and they give you 2 molar and they say how many grams is that. So we know that we cannot use the volume and the concentration to get directly into the grams. What do we have to go through first? You can't use the volume and the concentration to get directly into grams. What do we have to get through first? Okay. All right, so we've got moles is equal to molarity times liter. Now the problem is the data given. Can we use those two numbers? As is. No. The molarity is the easy one. 2.00. Now why did I put these in brackets? It's molarity. What do I have to do to my volume? So 0.515 liters. And that gives me how many moles? And I'm just going to say of F. I don't feel like writing the whole thing. Now, then we can say 1.03 moles of F. And then we got to go from moles to grams. And what's your molar mass of ethanol? 46.08. And that gives me how many grams? 47.5 grams of F. Now, that's our answer to part 1. Does that make sense? Now, I'm going to go into part 2. Can I go or do I need to wait? Go ahead. Really, honestly, it would be A, grams, B, or molecules, C, volume. It would be different parts. Okay? Chapter 4. All right. Now, so the next one. So 47.5 grams of F, and I need to get from grams to molecules. Now, my first question is, when I taught this last year, I taught this as in atoms or molecules. Why can you not ask how many atoms of ethanol there are? Because ethanols are molecules. It's not one single atom. Now, let me ask you this. Could they ask you how many atoms of carbon are in this thing? Yeah, and I'm actually going to do that. We're going to extend this problem in just a second to show that. Okay? Atom is a thing. Molecule is a group of those things. Ethanol is a group, so it has to be a molecule. One carbon. Yep, it will be how many carbons are in this thing. Sir. Yeah. Yep. All right, so here's the deal. So let's follow this. So if I have grams, can I go directly from grams right into molecules? Who do I have to get to first? Moles. Okay? No. We do? Oh, okay. Well, let's start there. I was being an idiot. My bad. Okay. So let's start back over. So I have one. I have 1.03 moles of F, and now I need to go from moles to cules. The molecules, very good. So we know that in one molecule of any substance, how many molecules are present? 6.02 times 10 to the 23rd. Okay? Now, so this is, how many molecules do we have? Okay? So there's 6.20 times 10 to the 23rd molecules of F. Now here's what I'm going to do. I'm actually going to add an extension part of this. What if part C read, how many atoms of carbon are present in this thing? Okay? That's what we need. So let's start with this. So I'm gonna write this all in red. So I'm starting with moles, 0.3 moles of F. Now, we know we need to get rid of moles of F. But I've asked this question all the time. To get from one thing to something totally different, what do you need? Mole to mole ratio. Now, this is not really a true mole to mole ratio. This is really a what? An atom to molecule ratio. So we're trying to get to moles of just carbon. Would you agree or disagree? Okay, Ryan, you write this down? Okay, so in one ethanol, how many total carbons are there? 2. Now I'm going to go ahead and throw this hypothetical in there. What if the question had read, how many atoms of hydrogen? How would your ratio have changed? Be very careful. It's 6. That is a good one. Okay? There are 6 of them. You have to add the other one. I know that's weird, but it's how it's set up. How would it have changed if it were asking about atoms of oxygen? It would be 1. Does that make sense? It would be a 1-to-1. But we're asking about carbon. I just wanted to throw the hypothetical in there. Now we have in 1 mole of carbon, there are Avogadro's number worth of atoms. Now, from the red formula to the blue formula right above it, what's the only difference? You have to go from moles of the compound to moles of carbon. Mathematically, value-wise, what would be the difference? You double it. Okay. What if it were hydrogen? What would you have done? Times 6. Sextuple it. No. This, and I'm going to write this in brown. If this were 6 moles of hydrogen. The way we got 6 is because there are 5 plus 1, which is 6. Okay? But again, we're not doing the 6. We're doing the 2. Okay? So, what is double 6.2? What is double of 6.2 times 10 to the 23rd? 1.2 what? So, the 2 things I want to focus on. Number 1 is, do you understand why we had to go from moles of ethanol to moles of carbon? No? Is there a no? You have to go from the compound to the atom. And remember, to go from one thing to something different, you got to use a mole to mole. Yes, no, maybe? I added that. I agree, that's not a question. I'm just adding this as a part of it. Because I'm hint, hint, wink, wink. You may want to know how to do this. Okay? Carbon, yes, ma'am. Oh, I've already asked that question. An atom is one thing. And molecules are made up of a bunch of atoms. You with me now? Yes, ma'am. The compound. How many of those, like if I handed you a bag full of ethanol compounds, how many ethanol compounds are in that bag? Bingo. make sense? Okay. Yes. Okay. You can never, ever, ever go from gram to gram of anything directly. Moles must always be the middle thing. To get from one side of anything to the other side of everything, the moles have to be involved. The moles is the bridge. If you're in something other than moles, you're more than likely going to have to go through the mole to get there. There are a few exceptions, and I'm not ready to teach you those yet, but there are a few. Yes, ma'am. No. You have to, yeah, you realize sort of, because the mole to mole has to be in front. Okay. Yes, sir. Yes. Yes, absolutely. But here's the thing. There No, 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 no. You can do that. You can absolutely multiply that blue answer by 2. But I highly doubt they're going to ask you the blue and then the red sequentially. They're going to ask you one or the other. So you would set up either one of these to get your answer. Does that make sense? Go ahead. I absolutely agree with that. I agree. Any other questions? You can divide it by 2. I agree with you. These are two, and I'm saying two as in TOO, as in also. They are two similar of questions to ask them sequentially. Okay. Now let's actually do the last part of this, and it says what volume of ethanol is dissolved in the water, and this is ethanol has a density of. So here's the deal. What's the question? Volume of ethanol. And then they give you this random thing called density. Now, we know the density is gram per milliliter. True or false? Now I'm gonna erase some of this just for space. Let me bump my eraser size up because I'm gonna need some of this. Some of you remember this. Some of you may not remember this. I hope that you do. The density triangle. Now, density is where in this triangle? Bottom left, what's always on top? Mass, and then volume. So according to this equation, what are we solving for? The volume. So if I pull this out, volume is equal to what? Very good. Mass over density. Now that you see this, how much easier has this problem all of a sudden become? It is a breeze. You've always got to remember that it can be broken down into easy steps if you know where you're starting and where you're ending. They gave you that density for a reason, right? They asked you a part of the density question, right? Now, here's the best news. Because it says volume, does it matter what unit that it's in? What is the volume unit given in the density? Milliliters. Is it appropriate to leave it as a milliliter? What if the problem had said how many liters of ethanol? You would have had to convert it, right? All right, so we know that the mass is 47.5 grams, and the density is 0.789 grams per milliliter. Now, I'm going to come back to this. Give me 1 second. As far as the units go, grams divided by gram per milliliter. We hate fractions. We definitely hate fractions and a fraction, right? How do we get that bottom fraction out? Multiply by the reciprocal. What is the opposite of G over ml? What happens? Leaving you with is that okay? Okay. So what is 47.5 divided by 0.789? Very good. Yep. Yep. Sir. Okay. It's a great question, and I have no clue the answer to that. It does absolutely make sense. I absolutely agree with that. Awesome. I don't worry about it. Don't try to get in Dustin's brain. It's not worth it. I don't know what I did with it. There it is. Thank you. I'm hiring a secretary if any of you would like to apply. There is no salary involved. No. As often as possible. Okay, so, moving on. What? Shh. All right, here we go. Number one. Now, there is a little note up here that I handwritten on your copies. It says, show how each of the following strong electrolytes. Now let's stop right there and let's talk about this because I want to make sure that when you read this, your brain picks up on these key words. Is strong electrolyte very important? What do we know about it? Okay, so we've got 100% dissociation. Now, we could also say ionization. We can say other stuff. This is other page, the other sheet. We're not doing the back, no. You don't know how to do it yet. I haven't taught you that yet. Say it again. Guys, just listen. Now, here's the deal. I'm going to add a new topic. I'm going to add a new little piece of some information to this. Whenever you hear the word 100% dissociation or ionization or strong, this is what I need you to think. Completion. Now, I know what you're thinking. Completion, okay? That sounds cool and all. We're going to talk about this over the next several weeks, and it is very important that you understand the difference between these two things. There is a difference in those two things. So somewhere on your paper, I want you to write down these things. And by the way, yes, this right here kind of divides the two. Stop. Just write it down for right now. I promise. Come back to your question. Don't get ahead of me. Okay. No, don't. Okay. And I'm forewarning you. This is going to cost some of you points because you're too lazy to pay attention to the details, or you just don't know. Okay. When you see this top arrow, this represents completion. And what that means is when the reaction begins, it goes until it stops. Okay? That means it goes and works and works and works and it just quits. It doesn't do anymore. And everything is used up. Is there potential for limiting a reaction to be left over? Yes. We're not talking about that. We're talking about what happens in the reaction. Stop. Excuse me. Excess. My bad. Excess reactant. Okay? Now here's the other part. This bottom one is the one that's going to get you. What this represents we will jump off into that deep swimming pool later on in this semester. I'm forewarning you now, in this chapter, these two things are going to come into play. And yes, they are specific. Yes, they are important. Just like when you see the brackets, what do brackets represent? Molarity. Yes, that is crazy specific, but yes, it is that important. So when you see these two arrows, yes, they are different from one another for a specific reason. So just a second ago, when you saw the word strong, you already connected it to 100%. Now we need add another tagline to that. So when you see strong, you know 100. Now you need to add what word? Completion. And that represents what type of arrow? One direction. Sir. Yes, they will look just like this. They will look just like that. No, that's legit. Um, I hold that thought. I don't know. There's a formula you can plug in. Okay, so let's go back to this. Now, so it says, show how each of the following strong electrolytes break into its component ions upon dissolving in the water by drawing molecular level pictures. The first thing that I wanted you to do was actually write the reaction. And all of these needed to be appropriate. So since they're strong, we know they're 100%, and we know they go to completion. So what type of arrow are we going to use? The full arrow, the one direction arrow. Okay, and I'm going to go ahead and just do this. Now, the first one is calcium phosphate. Now, if we show them in their ionic form, would you agree that calcium is Ca2 plus and phosphate is PO4 3 negative? If you left it like that, would you be right or wrong? Wrong. Remember I told you it needs to balance two ways. It needs to balance for atoms and it needs to balance for charge. So what is the entire charge in the left side of the reactant side? It is neutral. But if you look over there on the product side, what's the total charge? -1. That's a problem. Both sides have to be the same. They don't have to be neutral. They just have to be the same. Okay? So, how can I fix this? Very good. This is my 2-3-6 rule. Now, another way to look at it is it the exact same as your subscripts? Yes. Okay? All right, so that's going to be that one. All right, the next one is potassium, which is a group 1, plus nitride, which is a group 15, which makes it -3. Again, that is not appropriately balanced, so what do we need in front of the K? A 3 and anything in front of the N. No, fantastic. Okay, the other ones are Fe. Now, which iron was that? Very good. Iron was 3 plus, and the chloride is always what? -1, and that's not appropriately balanced, so what do? Add a 3 in front of the chloride. Fantastic. And here's the one that's going to get some folks. Strontium, what group? 2. Very good. So it's Sr2 plus, and then what's carbonate? Very good. Now, look back in your formula. Where in the world did my 2's go? They canceled out. You with me? Now, do you agree that this is pretty self-explanatory? The next part, it wasn't? What's wrong? Yeah, but it doesn't the handwritten instruction say write the... Yeah, break them for it all. Okay. Absolutely, you can. I just want you to look at it from all perspectives. So then it says you only had to draw A and B. And when you did this, I told you guys that you had to make it stoichiometrically correct. And I know some of you looked at me and said, I have no idea what that means. We'll just rock on with it. So the first one we had was Ca, help me out. It was 3. So what that means is when you draw this, is that it must be stoichiometrically congruent. That means your ions' charges must match the balance equation. So you had to draw it just like the products in your reaction. So how many calciums do I need to draw in this solution? Very good. So I'm going to draw them in orange. So I've got Ca2 plus, Ca2 plus, and Ca2 plus. Everybody good with that? Okay. All right. How many phosphates do I need? 2. PO4 3 minus, and I'm going to just add more volume to it. Now, if you had drawn it like this, would you have earned credit? You sure would not have earned credit, because what do you have to show? The water. Now, when you draw the water, is there an appropriate way to draw the water around these things? Yes. Very good. And the sizes must matter. Now, I didn't do a very good job of drawing those. I did a really bad job. I hate drawing the polyatomics like that because it's such a difference. But what part of the water faces the cation? Oxygen. All right, so I'm going to draw 3 waters around that one. Okay. I apologize. Yeah, that's fine. If you drew it like this, if you drew, that's fine. I like it. Now, how would the Mickey Mouse be turned against the anion? The hydrogen. So the ears would be touching it. It doesn't want to kiss it. Does that make sense? I like that. So Mickey Mouse doesn't want to kiss the negative things. It's turning its ears to it. Shut up. I didn't come up with it. Mason did. Okay. It makes sense. All right. Okay, that's a great question. Why are there 3 waters? Now, I'm going to go ahead and tell you this. Remember when we said we have to saturate the ions? And what that means is we have to surround the ions with water. In the past, Jamila, this is the important part. In the past, when the AP exam has asked students to draw this stuff, and every year they've asked them to draw stuff like this, I have seen a trend that it says with at least 3 water molecules. So I'm just kind of going with what I've seen them ask in the past. The major point is, do you want to draw just 1? No. So I'm just kind of training you with what I've seen them do. Does that mean that next year they won't say draw at least 5? No. But I've just noticed that the 3 is kind of what they've gone with. Yes, ma'am. That's why I only do A and B. Okay? Now, B's a little easier to deal with because you don't have a big polyatomic. All right, what is the compound again? Potassium nitride? Now, this is the one that you can really show the differences in. Because when you draw the ions, the cation and the anion, which one should be smaller? The cation, very good. So I need how many potassiums in this thing? Let me erase this because that was way too big. So I'm going to write a little bitty K. Okay, and then I'm going to make my nitrogen significantly larger. And I only need how many? 1. So I'm going to erase that thing and put it in a better spot. Okay. All right, so who's the Mickey Mouse going to kiss? The positive one. See? You fools are falling for it. Okay. Now, obviously, you don't have, I'm not going to spend the time to draw all of them around each one of them, but you guys get the point. All right, who's the Mickey Mouse going to turn his ears to? The mean negative one. Negative nitrogen. Oop, backwards. That was a, never mind, I'm not going to say that word. I'm not going to say that word. Nothing, you're good. All right, so we're good on all this. So let's go back to the problems. Number 2, calculate the molarity. And I like this question because you probably wanted to throw something at me when you read it. It says calculate the molarity for a 1.846 milligram sample of potassium dichromate is dissolved in enough water to make 433 milliliters of solution. So, again, this is the important thing. What's the question? Okay, so we should know by this point that molarity is equal to mole per liter. And this is why this is a jerk of a problem, because the 2 pieces of data, can either one of them be used as is? No, which one's the easy one to convert? Milliliters, okay? So we know that it's 0.0 433 liters of potassium dichromate solution. Now, there's two ways you guys could have done this, and I don't care how you did it. I'm going to do it the long way, just in case you need that help. Okay, so we're starting with 184.6 milligrams. What's the problem with that right off the bat? It's not in grams, so we can't jump right into our gram to mole conversion. So here's what I'm going to do. I'm going to say that there are 1,000 milligrams in 1 gram. You do not have to do that. If you went ahead and converted it to grams, just rolling the decimal, I'm totally fine with that. I don't care at all. In fact, that's probably what I would have done on a real test, but I'm just showing this just to show it. Okay? So then we have grams to moles. And in 1 mole, what's your molar mass? 294.2 grams. And that gives you how many grams? Excuse me, how many moles? Anybody get something different than that? The number of moles of potassium dichromate. Dustin? Justin? To the negative what? Sorry, Elizabeth. I heard somebody say, but I heard like people say, I didn't get that, so I just wanted to make sure. Okay. There we go. My apologies. My apologies. All right, so now this is in what we needed in, and so what will be your concentration? Third or fourth? Any questions on this? Again, these are the kind of dastardly things that these people do. Dastardly with a D. Okay. Now, I love number 3 because it gives that one ugly word that all of you hate. Describe. Okay. Good. That's the question that I want to hear, or the words that I want to hear. It says describe how you would prepare, which means give instructions, 7 liters of a 0.75 molar potassium dichromate from solid K2RO7 or K potassium chromate. So here's the deal. My point is when it says that you must start with solid potassium chromate, what unit must be given in your description? Grams. If it tells you you're starting from solid, you better give me a mass. You better give me my grams. So, how do you get your grams from the 2 pieces of data? Mole is equal to molarity times volume. So it's 0.750 times 7.00 liters gives me how many moles? Which is equivalent to how many grams? Because I'm not doing all that math. 1,020? Wow. So, when you say you explain this, and you can tell me if I'm right or wrong, it should be something similar to this. You would mass out 1,020 grams, or how many of you went the fun way and said 1.02 kilograms? Anybody say kilograms? Losers. Yes, ma'am. Gotcha. Or were you in it last year? Your name was on the list. Or are you going to show up this year? What was I asking? Oh, 1.02 kilograms. And again, if you didn't, that's fine. You could say 1,000. Mass out 1,020 grams of potassium chromate on a digital balance in a weigh boat. Okay. Pour the solid into a 7-liter volumetric flask. Say that again. Yeah, potassium dichromate into the 7-liter volumetric flask. Excuse me, chromate. Pour enough warm distilled water in the flask to do what? Completely dissolve the compound or the solid or potassium dichromate by swirling. Very good, by swirling. Then fill the rest of the flask up to the line, mark, or etching on the neck. And then the final sentence must be, this would have made, or you would have made, a 0.075 molar potassium, a 7 liters of 0.75 molar potassium chromate solution. Does that sound good? The explain part is easy once you know okay. In just a second. Okay. Mass out. And then tell me how much and what it is and what type of tools you used. You would have made, or this would make, 7 liters of a 0.75 molar K2CR04 solution. So you're just you're retelling me what you just did. Everybody good with that? All right, I just now realized it, but we are not able to do 4 or 5 either, which is actually perfect because we're out of time. Because tomorrow we're going to work with stock and dilute solutions. Stock. Well, like the problems.